Hi students, good morning. After alcohol, we are going to discuss today about phenol, another interesting topic. So what is phenol? If you see phenol is also known as carboic acid. Okay, there is another name for phenol, that is carboic acid. So what is phenol? If NOH functional group that is attached to a benzene ring, that is an aromatic system, you will get a phenol. So this is phenol. And how we will name phenol? It's very easy, just like alcohol, how we named the same manner, we can name alcohol also. Sorry, phenol also. How we will name it? Give lowest number to OH group while numbering. Okay, I will give you one example. This is one example. Okay. This is one example of phenol. So what they are saying, give lowest number to OH group. So you have to start numbering from wherever OH is there. From there, you have to start numbering 1, 2, 3, 4, like that. Okay. Name the branch first. You have a branch here. So you have to name this branch first with the position. Which position is the branch? Third position. So 3 methyl. And then the rest of the part we know the name is phenol. Okay, this is the naming. Very easy, right? Now, dihydroxy derivatives of benzene. If you have two OH group on the benzene ring, we cannot name it as phenol. So it is named as the ring is benzene ring, benzene. And which positions are the alcohol? 1 and 2 positions. So 1, 2. And this is diol. Okay, 2 OH group is there. So we will write it as diol. Okay, this is the way we will name it. We can see more example now. Okay. Look at this example. Here, if only OH group is there, no substituents are there, then what we will do, then we will name it as phenol only. Okay, we will name it as phenol only. Now, if we have an OH group and CH3 group, we will number from here 1, 2. Okay, so this is named as 2-methyl phenol. Here also 1, 2, 3. 3-methyl phenol. Here also 1, 2, 3, 4. 4-methyl phenol in this way. Okay, so this is named as cresol because phenol with the CH3 group is called cresol. And depending upon where the CH3 group is, its name. These are the common name. Cresol is a common name. So we know that if you have phenol, based on the position of phenol, we can give the name for each position. Okay, this is OH group. Adjacent to OH group, these two position is called ortho position. These two position is called meta position. And just opposite to OH, the position is called para. Okay, so here adjacent position of OH is CH3, so that is ortho position, so it is called orthocresol. Okay, now after this adjacent position, next position, that is second position from OH, that is called meta, right? So this place is called meta, so that is why it is called metacresol. Okay, just opposite to OH, that is called para position, and this is called paracresol. Okay, now dihydroxy, because if two OH group is present, we cannot name it as word phenol. So what we will name? First, you will write the ring benzene. Which and which position? First and second position, 1, 2 diol. Here 1, 2, 3, 1 and third position, so 1, 3 diol. Here 1, 2, 3, 4, 1 and fourth position, then it is benzene 1, 4 diol. And all of these are having a common name. This is called a catechol, this is called resorcinol, and this is called a quinol. Okay, these are the common names. Now, Let us see the preparation methods of phenol. There are different methods of preparation. Already we have learned one method. In haloarenes, we have learned one method. That is what we are going to discuss first. This is already learned in haloarene. The haloarene will undergo very rarely nucleophilic substitution reaction. So this is the nucleophilic substitution reaction of haloarene, and we understand that rarely it will undergo nucleophilic substitution. Drastic conditions are necessary for the nucleophilic substitution reaction. So this is the nucleophilic substitution reaction of a haloarene. When it reacts with the sodium hydroxide, it is using drastic conditions, high temperature and pressure is needed. Then it will be converted into corresponding sodium phenoxide, ONA, okay, the corresponding sodium phenoxide, okay. So after that, this sodium phenoxide we have to convert into OH, okay. So this step you have to learn well, because everywhere we are going to learn this step, okay. Whenever you are getting sodium phenoxide, then just undergo acid hydrolysis, okay. If you undergo acid hydrolysis, quickly it will be converting into phenol, okay. So phenoxide, sodium phenoxide, okay, when you undergo acid hydrolysis, you will get a phenol. This step is very important. Everywhere we will use the step, okay. So first we will convert the haloarene to sodium phenoxide, and then sodium phenoxide undergo hydrolysis, acid hydrolysis, and we will get the phenol. That is the first method, and this method is called nucleophilic substitution reaction of a haloarene, okay. Now, next method is from benzene sulfonic acid. So first we have to convert benzene to sulfonic acid, right? That is the first step. Let us see that. Here, benzene is there, right? Benzene, in order to convert into sulfonic acid, benzene is treated with the oleum, okay? Fuming sulfuric acid, it is oleum, it is treated with S2O7, it is treated with the oleum, and then this will convert benzene to benzene sulfonic acid, okay. And I said you the step, sodium phenoxide step is everywhere. So what they are doing after that, this, whenever it is formed, benzene sulfonic acid is formed, this benzene sulfonic acid will react with the sodium hydroxide, molten sodium hydroxide. So it will be first converting into sodium phenoxide. It will be first converted into sodium phenoxide, and that sodium phenoxide will undergo, this is the second step, will undergo acid hydrolysis, and so the step is repeating here also, okay. So first H2S2O7, benzene is reacting with the oleum, and that is called fuming sulfuric acid, very concentrated sulfuric acid. When you dilute this oleum, we are getting sulfuric acid, okay. So what is this? Benzene is reacting with the oleum, and we are getting benzene sulfonic acid that will react with the molten sodium hydroxide and form sodium phenoxide, and after that what will happen? It will undergo hydrolysis to get acid hydrolysis to get phenol, okay. Now next method, let us discuss from cumene. So what is cumene? Cumene is a hydrocarbon, okay. So let us see the reaction. So this cumene, this is cumene, this is a hydrocarbon, benzene ring with the this substituent is there, and that will undergo oxidation, okay. When it undergo oxidation, oxygen will add up, right? Oxidation means oxygen is going to add up, where the here 2 oxygen is add up, okay. So it will get cumene hydroperoxide. So from cumene we are going to get a cumene hydroperoxide. From cumene hydroperoxide we are getting, and that cumene hydroperoxide will undergo acid hydrolysis. So here directly it is not converting into sodium phenoxide, directly it will undergo hydrolysis and we are going to get a phenol and acetone. So for the preparation of not only phenol, for the preparation of acetone also we can use this particular method. Okay. And cumene we are using, and when cumene, phenol is manufactured from cumene, right? Cumene is oxidized in the presence of air to form cumene hydroperoxide, okay? And it is converted to phenol and acetone by treating it with a dilute acid. That is acid hydrolysis. That is what we discussed in this reaction. Now, let us discuss about the physical properties, okay? What are the physical properties of phenol? So, if you take phenol, this is a phenol. If there is any side chain like CH3 or something, if the number of this carbon atom increases, what will happen? Intermolecular force of attraction increases and also boiling point increases. Okay. The phenol, as we know, it is having hydrogen bond, just like alcohol. Phenol is also having hydrogen bond. So look at the hydrogen bond. We know that alcohol is having hydrogen bond. Just like that, phenol is also in between phenol molecule, also hydrogen bond is there. This is the reason why always phenol is having high boiling point compared to ethers, compared to other hydrocarbon which is having the same molecular mass. Okay, so if they're asking you about what is the reason why phenol is having high boiling point or alcohol is having high boiling point, the reason is same, because they have hydrogen bond, which is the strongest intermolecular force of attraction. Okay, so now let us see the solubility. Same answer. It is soluble readily in water. Phenol is soluble readily in water. What is the reason? Because it will form hydrogen bond with the water. Let us see how it is forming hydrogen bond with the water. Look at this. With the water, it is forming hydrogen bond. Okay, we have to actually show this lone pairs, charge separation, this delta plus. Okay, lone pairs are here. So it will form hydrogen bond with the phenol. Okay, that is the reason why it is completely so. But as the number of alkyl group is there, if it is increasing, what will happen? The solubility will decrease, because alkyl group is, yes, water. It is not water soluble. Okay, hydrocarbons are not water soluble. Now, let us see the acidity of phenol. Let us see whether phenol is acting as an acid or not. We already know that what is an acid? Acid is a substance which will donate H plus ion, right? The acid is a substance which will donate H plus ion. So acid is a substance, when it reacts with metal, it will produce hydrogen gas. These all are the properties of a metal. So acid is a substance which will donate H plus ion, and acid is a substance which will react with metal and produce hydrogen gas. Okay, and its corresponding salt. Let us see how phenol is reacting with the metal. Okay. Look at this reaction. Here what is happening? Phenol is reacting with the sodium and producing hydrogen and corresponding sodium phenoxide salt. So it is an acid. It is behaving just like an acid. Okay. And what is the reason why it is acting as an acid? Let us see that. Okay. Now look at the phenol structure. If you see the phenol structure, this is phenol, right? And it is having lone pair of electrons also, this oxygen atom. Okay. And this hydroxyl group in phenol is directly attached to sp2 hybridized carbon. Which is sp2 hybridized carbon? Carbon is here. 1, 2, 3 sigma bond is there. So this hybridization is sp2 hybridized, and which is attached to the benzene ring. And this carbon, sp2 hybridized carbon, should be highly electronegative. Okay. and it will withdraw or drag electron towards this ring. Not only this carbon, the entire ring. Okay, so the entire ring is dragging. It will act as an electron withdrawing group. It is sp2 hybridized carbon, so its electronegativity is high. So this electron present on the oxygen atom is dragging towards the ring, so that the oxygen will get a positive charge. Okay, and already we know that OH bond is polar. If OH bond is polar, it is easy to remove this hydrogen atom. Okay, so benzene ring which act as an electron withdrawing group. Due to this, the charge distribution on phenol molecule in its resonance structure causes the oxygenous OH group to be positive. It will be positive. That is what I said. What in the phenol, this carbon atom present is sp2 hybridized, so it will drag electron from the oxygen atom, and the oxygen atom will get a positive charge. So the positive charge on the oxygen will increase, and not only this, it will undergo a resonance structure. So let us see the resonance structure of. Let us see the resonance structures of phenol. Look at this. Already we discussed the lone pair present. Okay, the lone pair present on the oxygen atom is dragging towards the ring, so that it is getting a few resonance structures like this, and oxygen is getting a positive charge over here. Okay, and due to the higher electronegativity of sp2 hybridized carbon, we already discussed this, the carbon of phenol which is attached to OH, okay, that is attached, electron density decreases on oxygen. What is the reason? Because it is dragging towards the ring. This increase the polarity. Already we discussed that will increase the polarity of the bond and result in an increase in ionization of bond than that of alcohol. Okay, so what will happen? It is easy to remove hydrogen ion from this particular, because as the positive charge on the oxygen atom increases, the polarity also increase. Okay, as the polarity increase, OH bond increase, it will be very easy to remove the H plus ions. Okay, so we already discussed acid is a substance which will donate H plus ion easily. So easy removal of H plus ion is possible because of this reason. I'm explaining that again, very important point it is. What we have to write? We have to write phenol. In phenol, the OH group is attached to a benzene ring. Upon that, attached to a carbon atom which is sp2 hybridized. So the electron lone pair present on the oxygen atom on OH group, that will be dragging towards what? That will be dragging towards the ring, so that it will get resonance structures and oxygen will get a positive charge. As the positive charge on the OH group increases, the OH bond become more polar. Okay, when it is more polar, the dissociation of H plus ion or the removal of H plus ion become more easy. So it will be acting as a better acid than corresponding alcohol. Okay, so alcohol is not having such a system. If we OH group, it is not having an electron withdrawing group there. Instead, it is having what? Electron releasing group. Actually, this electron releasing group is increasing the negative charge on the oxygen atom. Okay, so it is decreasing the polarity. So if we are comparing phenol with alcohol, okay, phenol is more acidic. Phenol is a strong acid compared to that of alcohol. Okay, there are more reasons. Okay. So what is the evidence that it is stronger than an alcohol? Phenol is stronger acid than an alcohol. So we are going to see the evidence for that. Whenever a phenol alcohol is reacting with, whenever an alcohol is reacting, it will be dissociate. Sorry. it will be dissociated as whenever H plus ion is removing from an alcohol, it will be dissociating as RO minus plus H plus. Whenever a phenol is dissociating, it will be converting into O minus plus H plus, right? So the acidity that depend upon the stability of RO minus or this phenoxide ion formed. Okay, it depends upon the acidity depends upon more stability it is having. If the phenoxide ion is having more stability, means it will be more acidic. Okay, so here we are not in the case of phenol. If you are checking the phenol, in the case of phenol, we are not getting any resonance structures, no resonance structure. This negative charge is here only. Okay, it is localized on the oxygen atom. Okay, but if you are thinking about the phenol, what is happening? It will undergo resonance. Okay, so this phenoxide ion undergo resonance and it is having more resonance structure, so it is having a stability. Okay, now if you compare the stability of phenoxide ion and phenol, phenol is less stable than phenoxide ion. What is the reason? Because in the case of phenol, we can see in the case of phenol, we already seen the resonance structures, right? In the case of phenol, during resonance, what is happening? This bond is shifting to this position, this bond is shifting to this position. So oxygen is getting a positive charge during resonance, right? And this bond is shifting to here, means negative charge also here. So there is a charge separation in the overall resonance structures. If charge separation is there, stability should be less. Okay, but in the case of phenoxide ion, you can see that how the resonance is happening. This negative charge is shifting here, this is shifting here. So the next resonating structure will be like this, double bond O. Here also double bond is there. This lone pair is shifting here, double bond is here. Double bond O and then minus. So only negative charge, only one charge is spreading throughout, right? Only one charge is spreading throughout. Here there is a charge separation, two different charges are there. If more than two different charges are coming in, stability will be less. But here only one charge is there, a single charge, negative charge only is there, so that the stability of this molecule will be higher than that of the phenol. Okay, since the intermediate, that is the phenoxide ion formed after the removal of H plus is stable, it is more prone to remove H plus ions. It can easily remove H plus ion because this is more stable than phenol, right? But here the negative charge is localized on the oxygen atom, no resonating structure. So the removal of H plus ion is not easier like in the case of phenol. Okay, that's the reason why phenol is more acidic than the corresponding alcohol. Okay, we discussed this. See, the alkoxide ion, the negative charge is only the negative charge is spreading, but in the case of a phenol, more positive and negative charges on the same resonating structure, so its stability should be less compared to that of phenoxide ion. Okay. Now, if you think about substituted phenols, so let us go back to phenol, resonating structures of phenol. What are the different resonance structures of phenol? Phenol resonating structure we already have learned. Okay, these are the different resonating structures. In this different resonating structures, we can understand that the negative charge is coming at ortho position and para position. So the negative charge is more on ortho and para position if it is resonating. Okay, so the negative charge is concentrated on 2 ortho position and para position from this figure. Okay, now if you substitute the phenol with an electron withdrawing group, what will happen? Electron withdrawing group. So it will withdraw. Suppose NO2 is an electron withdrawing group. If you are substituting electron withdrawing group at ortho position, you have to substitute either in ortho position or in para position, because the electron density is more in ortho position and para position. So if you substitute NO2 group in ortho and para position, what will happen? It will drag electron density towards that, so that the acidic strength still increase. The acidic strength still increase. So when it is dragging electron towards it, the positive charge on the oxygen atom will increase, right? Because the electron is more dragging towards the ring. Okay, but when if you have a substituent like electron releasing group like CH3, if you have a substituent like CH3, it will release electron towards the ring, so that the dragging of electron from the oxygen atom decrease. Okay, that we become less because there is some electron releasing group present in the ring. So electron releasing group decrease the acid strength, and electron withdrawing group increase the acid strength of the phenol. Okay. Now, next is some reaction. So let us see esterification reaction. What is esterification reaction? Phenol react with, we know that the reaction with the carboxylic acid it is, or we can react it with anhydrous acid. The same reaction we learned in alcohol, acid anhydride, or it will form esters. Let us see that reaction. So either alcohol, same reaction I already discussed in the last slide, how they are reacting. If it is an alcohol or an phenol, same way the reaction will undergo. Okay, look at phenol. This is phenol. Phenol is reacting with an acid, means R dash C double bond OH. So water will be removing from here, and it will be in the presence of only acid, it will take place. It will be converting into corresponding R dash C double bond OO ester. Okay, then this R group. Okay, that is what happening here. So the removal of water is taking place in this way. Acid anhydride and acid chloride, it will react with the phenol, and you will get the corresponding ester. All of these are esters, but you will get different products when it is reacting. If you are reacting with a phenol, you will get a ester, and phenol is reacting with a carboxylic acid, you are getting ester and water. If it is reacting with an acid anhydride, you are going to get one ester and one acid. And if it is reacting with acyl chloride, instead of H2O, you will be getting HCl. So why we are using pyridine? We discussed already. We are using pyridine in order to neutralize the acid formed. Okay. So here also the rate of the reaction, the yield of the reaction, we can increase by removing water, because it is a reversible reaction. Whenever you remove water, it has a tendency to form more and more. The equilibrium will shift towards, or the reaction will shift towards the forward direction. Okay, so more and more yield we will get. Here also, if you are adding pyridine, it will neutralize HCl, and so that the reaction will shift to this direction, right? Now, the preparation of salicylic acid. How the salicylic acid is treated. This is a very important reaction, preparation of salicylic acid. Salicylic preparation of aspirin from salicylic acid. Okay, salicylic acid means phenol with a COH group is called a salicylic acid. When it is reacting with an acid anhydride in the presence of an acid, it will be corresponding, it will be converting into the ester, right? Already we discussed ester formation. It will be converting into the corresponding ester. That is called aspirin, and you will get another acid. So it is used for the preparation. This phenol is used for the preparation of aspirin. That is one important use of phenol. Okay. Now, there are reaction of carbon where the carbon oxygen bond is breaking, that we will discuss later. That is the reaction of phenol with the zinc. Okay, so first we will discuss about the electrophilic substitution reaction. Okay, OH group is ring activating group because it is having a lone pair that will be directing towards the ring, so that it is a ring activating group, and also it is ortho para directing group. Okay, these two are important: ring activating group, ortho para directing group. Let us see the nitration reaction. So here it is undergoing nitration. How it is nitration means nitrating mixture we are using, right? Dilute nitric acid at, here we are using dilute nitric acid at a very low temperature. So what we are getting, ortho para directing group it is. So ortho position 1 NO2 and para position NO2. So what is the reagent we are using for nitration? Dilute nitric acid. Last time we used nitrating mixture, that is concentrated nitric acid and sulfuric acid. Here in phenol we are using dilute nitric acid. So we will get orthonitrophenol and paranitrophenol. Okay. Now, the ortho-para isomer can be separated. We can easily separate it by steam distillation. Orthonitrophenol is steam volatile due to intermolecular hydrogen bonding, while paranitrophenol is less volatile due to intermolecular hydrogen bonding. So there will be intermolecular hydrogen bonding present between paranitrophenol, and in orthonitrophenol, in between OH and NO2, there will be an intermolecular force. So intramolecular, within the molecule, there will be a hydrogen bond. I can show you that. Look at this. In orthonitrophenol, the hydrogen present in the phenol and the oxygen present in the nitrogen, this nitrate group, NO2 group, that must have form a hydrogen bond. This is called a intramolecular hydrogen. Within the molecule, the hydrogen bond is forming. So this is intramolecular hydrogen bond. So molecular association is not taking place here because within the molecule it is. But this is between the molecule. One paranitrophenol will form intermolecular force in between the molecule with another paranitrophenol. So this will result in molecular association. So it is, which is steam volatile here? The ortho and para isomer we can easily separate because orthonitrophenol is steam volatile. Why orthonitrophenol only form intramolecular hydrogen bonding, no molecular association here. The molecular association is happening in paranitrophenol. Okay, that is why it is not a steam volatile. Okay. And if you are using, there we were using dilute nitric acid. If you are using concentrated nitric acid, we are getting an important product here that is called picric acid. Okay. So the phenol is also used for the preparation of picric acid. We already discussed aspirin preparation. We are using as phenol, and same like that the phenol is also used for the preparation of picric acid. If you use concentrated nitric acid, all the ortho position and para position NO2 group will substitute and we will get picric acid. Very important compound. Okay. Next reaction, halogenation reaction. What is halogenation reaction? On treating phenol with bromine, different reaction products are formed under different conditions. Actually, when the reaction is carried out in a solvent of low polarity, such as CHCl3 or CS2, usually CS2 we are using at low temperature, monobromophenol. So in order to get monobromophenol, we are using what? CS2 at a low temperature. So ortho and para position, you will be getting the bromine substituent. Okay. Usually, the halogenation, we know that it will be taking place in the presence of a Lewis acid like FeBr3, okay, which polarizes the halogen molecule. So in case of phenol, the polarization of bromine molecule take place even in the absence of Lewis acid. So that is why we are not using Lewis acid here. It is due to highly activating effect of OH group. Very important. OH group is highly activating because its lone pair present on the oxygen atom is directing towards the ring, so that it is highly activating. Because of that, the bromine doesn't even need the Lewis acid to react. Okay, it will even react in the presence of CS2 at very low temperature, 273 Kelvin. Okay. So when phenol is treated with the bromine water, what will happen? Just like a picric acid, all ortho position and one para position bromine will substitute. Okay. This is actually a precipitate. We will get it in the form of a white precipitate. Okay. Next, Colb's reaction, another important reaction. Phenol, when react with sodium hydroxide, we are getting phenoxide that we have seen. That phenoxide is more reactive than phenol towards electrophilic substitution reaction. So it will undergo electrophilic substitution with even carbon dioxide, a weak electrophile. Okay, so it will result in the ortho-hydroxy benzoic acid is formed as main product. Okay, let us see that. So phenoxide ion is generated by treating the phenol with the sodium hydroxide. That is even more reactive than phenol towards electrophilic substitution reaction. That is what we are going to see in this. So carbon dioxide is a weak. Actually, this carbon dioxide is actually a weak electrophile. Even then it is reacting with the phenoxide ion, because phenoxide ion is highly reactive towards electrophilic aromatic substitution reaction. Okay, it is a named reaction, so it is very important. So whenever OH is reacting, this reaction is very familiar reaction. It is converted into ONA. Then that is treated with the electrophile carbon dioxide, okay, and followed by hydrolysis. So when you react it with carbon dioxide and undergo hydrolysis, it will convert into the corresponding salicylic, preparation of salicylic acid. We can prepare salicylic acid using phenol. These all are the uses of phenol. Okay, now another important reaction, Tumor reaction, very important named reaction. If you treat phenol with chloroform in the presence of sodium hydroxide, CHO group is introduced at ortho position. Okay, and this reaction is called a Tumor reaction. The intermediate substituted benzal chloride is hydrolyzed in the presence of alkali. We know that will convert into the corresponding acid. Okay, so let us see. This is phenol that is reacting with the chloroform, CHCl3 and aqueous sodium hydroxide. So when it is reacting with corresponding phenoxide plus CHCl2 will be forming here. CHCl2 will substitute over here. And when you treat it with sodium hydroxide, again, it will be CHCl2 will be converting into CHO, aldehyde group. When you undergo hydrolysis of aldehyde, you will get salicylaldehyde. Okay, not salicylic acid, salicylaldehyde. So for the preparation of salicylaldehyde, just now we prepared salicylic acid. Now for the preparation of salicylaldehyde also we can use phenol. What we will do, phenol will be reacting with the chloroform in the presence of sodium hydroxide. So we will get an intermediate that will be reacting with the sodium hydroxide again, and then we will get the the CHO group will be introduced at the ortho position, and when you undergo hydrolysis, what will happen? ONA will be converting into OH, and we will get salicylaldehyde. Okay, Glimmer reaction is very important. Now, I said you, there will be CO bond breaking. One reaction is there, that is reaction with the zinc. So when it reacts with the zinc, you will get benzene and zinc oxide. Very, very important reaction. Reaction of phenol with the zinc test. Here OC bond is, CO bond is breaking, okay? And we will get benzene. Preparation of benzene from phenol. React with the zinc powder, we will get benzene and zinc oxide. Now there is one oxidation reaction also. Okay, oxidation of phenol with the chromic acid. So when the phenol is reacting with the chromic acid or sodium dichromate, in the presence of an acid, it will be converting into benzene. Quinone preparation is also very important. Phenol is used to make benzene quinone. How? Oxidation with the sodium dichromate, and it is actually a orange color substance, sodium dichromate. In the presence of acid, it will be converting into benzoquinone. Okay. Now, what are the important uses? Phenol is used as the one of the starting material for the synthesis of many chemicals. What are the chemical? Salicylaldehyde, salicylic acid, picric acid. Okay, so many pharmaceutical drugs, explosive material, and plastic polymers. All this we are preparing using this phenol. Okay, phenol are one of the starting material for the formation of azo dyes also. Okay. We amine chapter, when we are learning, we will learn how to make acidizen also. It is also used for the preparation of what? Salicylaldehyde, salicylic acid. Okay, so many things we are preparing using this phenol. Okay, that's all for today. One more thing is there, one more method of preparation is there. We discussed only 3 methods of preparation. We will get benzene from diazonium salt also. How we are getting benzene from phenol from diazonium salt? Actually, a diazonium salt is formed by treating an aromatic primary with the nitrous acid. Let us see that reaction. If you look at this reaction, you can see aniline is treating with this is aniline when it is treating with sodium nitrite and HCl in 0 degrees Celsius, 273 Kelvin, it will be converting into benzene diazo, because N2 is present. That is why it is called a benzene diazonium chloride. When it treated with water, warm water, it will be converting into what? It will be converting into phenol, nitrogen, and HCl. Okay, that's all for today.